Hello class, welcome back to Physics 2. This is Sir Alex and today we'll be discussing capacitors and capacitance. So no nakaraan we discussed about electric potential and electric potential energy. This time it's basically the application of the principles we've learned about electric potential and electric potential energy. So let's start. So for our lesson, we'll start discussing about capacitors. So what are capacitors? So if you can see here, it's a picture. These are some examples of capacitors. You might have seen them somewhere in your house, napakalat-kalat somewhere. But the use of these are very important in a lot of electronics. Uh, what we do with them is we basically use them to store charges. So, mamaya ipapakita ko and explain ko on how we use these capacitors to store charges. Also, capacitors usually consist of two non-touching conductors of any shape. I will show later in mamaya how you can visualize how these capacitors are used and what are these two non-touching conductors. And usually, yung two non-touching conductors na ito are separated by dielectric. It's an insulating material that helps increase the capacitance. Later, I will discuss what capacitance is. But usually, the two non-touching conductors inside the capacitor are separated by what we call a dielectric material or just basically dielectric. Pinakasimpleng example ng isang capacitor is just a parallel capacitor, which we'll be discussing a lot for this lesson. So how do capacitors store charges po? As you can see, there's a picture here in a GIF or GIF, I don't know how you guys pronounce it, on how charges are stored in a capacitor. If you look at the picture right here, so these are your two parallel plates or two parallel metals, and they're separated by an insulating material that we call dielectric. Kung mapapansin nyo, yung dalawang plates are electrically charged. One plate is negative and the other plate is positive. So this is how capacitors store charges. But later I will explain how this phenomenon works. And we usually use this symbol to denote or when we talk about capacitors. So once connected with the battery, the two metals can store charges. So example, we added a voltage. So think of this voltage right here as a battery. And we attach a wire from one terminal of the battery to one plate and the other side of the battery or the other side of the terminal or the other terminal of the battery to another plate. What happens is that the negative charges gets attracted to the positive terminal end of the battery. So halimbawa dito sa moving picture. So you can see this is the positive side of your battery and this is the negative side of your battery. Kung mapapansin niyo, yung negative charge from the plate moves as it gets attracted to the positive side of your battery. And then the negative terminal part of the battery, this part, which is negative, repels the negative charge and it moves to the other side of the plate. So ano nangyayari? Basically, negative charge keeps moving from one side of the plate to the other side. And as this side right here loses negative charges, it becomes positive. And then the other side of your plate, as it accumulates negative charges, it becomes more negative. And that is how a capacitor stores charges. One plate becomes more electrically positive and one plate becomes electrically more negative, all because of the movement of the negative charges to the battery that we attached. So furthermore, another thing that you guys want to remember is that the magnitude of one plate is always equal to the magnitude of the other plate. So for example, this negative plate right here is negative 10 coulombs in your capacitor. The positive plate will always be positive 10 coulombs as well, even if the two plates does not look the same or they have different sizes or different shapes, because the same amount of negative charges that leaves one plate will have the same amount of negative charges that will go to the other side of the plate. So the negative and the positive plates will always have an equal magnitude. Second, the transfer of negative charges does not continue forever. There will come a point that the negative charge will stop moving from one side of the plate to the other, simply because the whole system wants to be in balance. And there will come a time that this charge right here is an example. Just think of this negative dot that I'm moving right now. Will come a point that this negative charge will be both equally attracted to this positive plate and to the positive terminal of your battery. And when that happens, when it's equally attracted, it stays there. It doesn't move anymore. And when it doesn't move, the transfer of the electron basically stops. And what happens is that all the charges that have moved will sit there. It will stay there. So meaning, even if you remove this battery, the positive charge and the negative charge will stay where they are. Okay? Normally then, the negative charge would want to move because it wants to restore, especially if you remove the battery, the negative charges would want to come back to the positive plate because it wants to keep the system balanced. However, because of the dielectric material that we have, it keeps the two plates from touching. And since they're not touching and we remove the battery, there's no pathway for the negative charge to move back to the positive plate. So that's how we store the charges. So I hope I explained that clear, because this principle is important in understanding how we solve capacitance. So not all capacitors have the same storage capacities. So meaning one capacitor may be able to store a lot of energy, a lot of charges, and one capacitor may store lesser charges. And all of that depends on what we call a capacitance, or the capacitance of your capacitor. So what is a capacitance? Capacitance is the ability of your capacitor to store charges. So we mathematically define this capacitance as C, as the ratio of the charge of one of the plate and the potential difference between the two plates. So this is your equation for capacitance. So it is a very general equation. Capacitance of a capacitor is equals to the charge, or the value of the charge of one of the plate divided by the potential difference between the two plates. So where C is the capacitance of the capacitor, we usually write that in units coulombs per volts, or we use the unit farad from, as you probably could have guessed, from Michael Faraday. So we use the letter F to denote farad. 1 farad is equals to 1 coulombs per volt. Q is the value of the charge of one of the plate, which is usually C, or in coulombs. And V is the potential difference between the two plates, or which we use volts. So we have coulombs per volts. The voltage between the two plates. The potential difference between the two metals, or the two plates, exists for the mere fact that they have stored charges. Because one plate is negative and one plate is positive, the electric potential is higher on the positive, near the positive charge, while the electric potential on the negative charge is lower. And since there's a difference in electric potential, there is voltage between them. And it is useful to remember that if you let a battery to fully charge a capacitor up, the voltage between the two metals is equal to the voltage of the battery. I want you guys to remember this because sometimes when you solve problems and it gives you the voltage of the battery, usually you would assume that the capacitor is fully charged and that the voltage denoted on the battery is the voltage between the two plates or the two metals. And one thing that I want you guys to remember is increasing the charge of any of the plate will not increase the capacitance of the capacitor. Why is that? Simply because as you increase the charge, let's go back to your equation. Simply because if I increase the charge here, it will not increase your capacitance. Why? Because if I increase the charge or the value of the charge of one plate, the voltage will also increase. So as the charge increases, so the voltage increases, so the ratio between the two remain constant or remains the same. So the capacitance does not increase. So how do we affect the increase in capacitance? How do we increase the capacitance? And this is an important question because sometimes you want to have a capacitor that can store a lot of charges in order for us to use it in bigger mechanics or bigger tools or bigger gadgets. So one way to increase the capacitance is the area of the plates. If we increase the size of the area of the plates, the greater the capacitance. So the bigger the area of the plates, the bigger the capacitance, or uh, the bigger is the ability of the capacitor to store charges. Second is the distance between two plates. If we make our plates closer to each other, sorry, the capacitance will also increase. So meaning the farther they are, the lower your capacitance. The closer the two plates or the two metals are, the higher the capacitance of your capacitor. And third, the insulating material or dielectric between them. So I mentioned earlier, you tend to place something in between these two plates or two metals. And this material in between them is usually an insulating material that we call dielectric. So depending on the permittivity constant, which we use the epsilon, uh, in between these two plates, it will also change the capacitance. I would not explain how it happens, but I just want you to remember that the higher the permittivity constant or the epsilon of the insulating material or your dielectric, the higher the capacitance. So from all this relationship, we can derive an equation between all the factors. So the capacitance is equals to the permittivity of your dielectric times the area of your plates divided by the distance between the plates. So if we look at this, you can imagine if I increase the area because of the relationship, it's not an inverse relationship, it's a proportional relationship. As I increase the area, the capacitance increases. The same thing with the permittivity of the material or the dielectric. If I increase the permittivity of the dielectric, the capacitance will also increase. However, as you can see, since we have an inverse relationship to the distance of your two plates, the the smaller the number or the denominator is, the higher your capacitance. The bigger the distance is, the smaller is your capacitance. So this is your second equation in measuring the capacitance when we are dealing with the area and the distance and the permittivity of the dielectric. So earlier we only have C is equals to Q divided by V. So we have the capacitance is equals to the charge divided by the difference in potential in electric potential of the two plates. But this times when we are dealing with the area of the plate and the distance and the permittivity of the dielectric, we use this equation. Okay, so what is dielectric? I kept mentioning earlier, it's an insulating material in between them. So it's basically a substance used to separate the two metals of the capacitor. Depending on the material used, it could increase the capacitance of a capacitor. So here is a table of some examples of dielectric substances or materials. One of the some of the common ones. The first one is a vacuum. When we talk about the vacuum, or when we talk about air, it's basically the same. The permittivity is 0.885 times 10 raised to negative 11 coulomb squared per Newton meters. If you guys are sharp, you would have noticed that this is actually what we also call the permittivity of free space, which is epsilon naught. We've, we've kept we've talked about epsilon naught a lot of times in our class, and it's a constant number that you have used to measure the electric field. You've used it to measure your electric flux. So when we talk about the dielectric between two metals being a vacuum or air, or it being empty, we're basically talking epsilon naught. We are basically talking about permittivity of free space. Free space, there's nothing in between. Okay, so that's epsilon naught. And then the rest, you can have a glass which has a permittivity of 7 times 10 raised to negative 11 coulomb square per Newton meters. So when you are doing problems, usually these are given to you, and if I'm gonna give a homework, I'm usually or problems, I usually will give this table to you. You don't have to memorize this. So dielectric is often denoted by the material's permittivity, so we usually use epsilon when we are talking about dielectric. But also we can use what we call a dielectric constant, which we use the symbol or the letter K. So sometimes instead of permittivity epsilon, we are instead given the dielectric constant, which are two different things. I hope you guys will not confuse what a permittivity is and what a dielectric constant is. So this is a dielectric constant, and we usually solve for dielectric constant using the permittivity. So in order for us to solve for the dielectric constant of a material, we usually divide the permittivity of that material divided by the epsilon naught, or the permittivity of free space. So example, I want to measure glass. What is the K, or dielectric constant of a glass? I know that the permittivity is 7 times 10 raised to negative 11 coulomb squared per Newton meters. In order for me to get the K, or the dielectric constants, I just need to divide this number by this number. So that's how I get K. That's just it. It's the ratio of the permittivity of the material and the permittivity of the air vacuum. So get the permittivity of the material and just divide it by permittivity of free space, or epsilon naught. Something that I've already said we kept using since before, the electric field and electric fast flux, etc. So this is another table for the permittivity, the electric constant K of some of the common substance. As you have probably know by now, or if you can see by now, the vacuum in the air is usually denoted with K is equals to 1. So when we talk about vacuum or air, we usually say it's free space. There's nothing in between the two plates. Okay? We can also solve for K using the electric field, but we're not going to focus on this too much. But it's just something that I want you guys also to remember. So to measure for the dielectric constant using electric field, what you just need to do is find the magnitude of of the electric field without the dielectric, meaning a vacuum or air. So this is your electric field in air divided by the electric field with the material, or with the dielectric. So it's kind of like inverse here. So the permittivity of the material divided by the permittivity of free space, while here it's the magnitude of free space, or the magnitude of air in a vacuum, the magnitude of the electric field in an air or a vacuum divided by the electric field when you added a material in between the two plates. So remember that K has no unit. Also, when we are using the dielectric constants, it's always going to be either equal to 1, equal to, or greater than 1. Okay? It cannot be negative, it cannot be a 0. It's either 1 or up or higher. And using the equation for the dielectric constant, which is K is equals to the permittivity of the substance divided by the permittivity of the vacuum or air, or the permittivity of free space, and the equation for the capacitance C is equals to the epsilon, or the permittivity of your dielectric, multiplied by the area of your plate, one of your plate, divided by the distance between two plates. Then we can use the equation C is equals to the dielectric constant multiplied by the permittivity of free space, multiplied by the area of the plate of one of your plate divided by the distance. So this is your third equation for solving capacitance, and we usually use this when we are dealing with dielectric constants. When we are given the dielectric constant, or when they ask us to solve for dielectric constant, we can use this equation. There you go. So we use this to look for the capacitance using the dielectric constant K. Capacitance in a vacuum or air. So the capacitance in a vacuum or air, so meaning when I have two plates and there's nothing in between them. They're not touching, but there's nothing in between them but air or vacuum. And when we say vacuum, it means there's nothing there. Even air molecules is not in between them. So the capacitance we usually denote it with C naught is equals to the permittivity of free space, or the permittivity of air or vacuum, multiplied by A divided by the distance between the two plates, is the capacitance in vacuum. And this is the case because K and the constant, the electric constant for the vacuum or air is usually 1. So if I'm looking for the capacitance of a capacitor with nothing in between the two plates, then I just have to change this to 1. So I have this equation right here. If C is equals to, this is our equation earlier, then we can denote this equation. Sorry. The capacitance of anything is equals to K, or the electric constant, times the original capacitance. So how can I explain this clearly? So for example, I have a capacitor A, and this capacitor A has a capacitance of, let's say 1. Let's just say 1. Capacitance of 1, while there is nothing in between the two plates. And then I added something in between it. And I know that if I added something in between it, I added a dielectric. That dielectric has a dielectric constant K. So if I measure the new capacitance after adding the dielectric, I just need to multiply the original capacitance of my capacitor to the dielectric constant of the dielectric I added, and that will be my new capacitance. So this means that the capacitance with the dielectric is increased by a factor K. Inserting other dielectric other than air or vacuum increases the capacitance to an amount equal to the dielectric constant times the original value again. So this is, sorry, my throat is itchy, a very general relationship between the dielectric and the capacitor. Okay, so for example, you have a capacitor that has an original capacitance with 0 dielectric, meaning there's nothing in between its two plates, of C naught. If you added something in between that two plates, that dielectric that you added has a value of K, has a dielectric constant. And if you multiply that constant to your original capacitance, then you will get your new capacitance. You will get your new value with capacitance. And this new capacitance now includes the now includes the dielectric that you added. So from here we can denote that we this is how we know that in order for us to increase the capacitance of a capacitor, we just need to add a dielectric in the middle, because C naught, or the capacitance of a capacitor without a dielectric, is always lower it's always lower compared to when it already has a dielectric added to it, because as I mentioned earlier, K can never be zero, can never be negative. So since it's one and higher, this will C naught will always be lower than C in this relationship. Sample problem 10.1. A capacitor consists of two metal plates, each measuring 5 times 10 raised to negative 2 meters on a side. In between the plates is a sheet of mica measuring 1 times 10 raised to negative 4 meter. There's nothing, this is thin. The question is, what is the capacitance of this capacitor? If the charge in one of the plate is 2 times 10 raised to negative 8 coulombs, what is the B potential difference and C electric field between the plates? So how are we going to solve this? Using the given as formula solution format, we'll have the given of S is equals to 5 times 10 raised to negative 2 meters. So this is the measurement of one of the side of your plate. Again, you look, this is just one side, do not confuse. This is not the area, this is just one side of a plate. The distance between the plates is 1 times 10 raised to negative 4 meters, because that's the sheet, that's the dielectric in between them. And the charge of one of your plates is 2.0 times 10 raised to negative 8 coulombs. And they're asking, A, what is the capacitance of the capacitor? B, what is the potential difference between your two plates? And C, what is the electric field between the plates? So formula. Since we are given the distance and we are given one measurement of the side, meaning we can measure for the area and we can measure for the D, or we can measure for the capacitance using this formula right here that we discussed earlier. And to solve for V, the potential, we can use this equation, the very first equation that we discussed. And to measure the electric field, we can use an equation that we discussed in lesson 8 and lesson 9. We can infer the electric field using the potential difference, which is the electric field is equals to the potential difference divided by the distance traveled by, or the distance between the potential difference. So how are we going to solve this? For A, from table 1, we know that the permittivity of mica is 4.8 times 10 raised to negative 11 coulombs squared Newton meter squared. Therefore, we could use the equation this. So basically substituting all the numbers. So this is from the table. The permittivity of the mica. Mica is a insulating material. It's on a dielectric. And the area for a plate, basically any plate, is basically S squared. You multiply the side to itself, especially if it's a square, or length times width. Okay, and divided by, and this is the distance that we're given. So we know that the capacitance of our capacitor is 1.2 times 10 raised to negative 9 farad. Next, we could use C is equals to the capacitance is equals to the charge of one plate divided by the potential difference. But we're looking for V, we're not looking for capacitance because we already measured the capacitance. But this time we know Q, we know V, or we know Q and we know C. So we can rearrange the equation to solve for the potential difference between the two plates. C is equals to Q over B is equal, basically the potential is equals to the charge divided by the capacitance. So we are given that one of the plate has this charge, 2.0 times 10 raised to negative 8 coulombs, and divided by the capacitance we measure in letter A, then we get that the potential difference between the two plates is 16.7 volts. And lastly, we previously learned in lesson 8 and 9 that we could infer the magnitude of electric field using the potential difference. We have the potential difference and we have the distance between the two plates that is making this potential difference. Therefore, we can use the equation E is equals to the potential difference divided by the distance to solve for the magnitude of the electric field in between the two plates. So that's our problem 10.1. Continuing on. So this time, this equation right here, the equations that we have talked about so far only works on parallel capacitors, okay? But there are some capacitors that are spherical and cylindrical in their nature. And we have to use a different equation to solve for the capacitance for these types of capacitor. So far we've learned to solve for parallel capacitors. To solve for the capacitance of a parallel capacitor, we use these equations. The capacitance is equals to the permittivity of your dielectric multiplied by the area of your plate divided by the distance between the two plates, or the capacitance is equals to the dielectric constant of your material multiplied by the permittivity of free space, or the permittivity of air or vacuum, multiplied by the area of one of your plate divided by the distance between the two plates. To solve for spherical capacitors, we will use this equation. I'm not going to fully explain how we derive on these two equations, but I just want you to know and remember that this is the equation you use when you're dealing with spherical capacitors and cylindrical capacitors. So for spherical capacitors, we use this equation. The capacitance is equals to 4 pi epsilon naught, permittivity of free space or permittivity of air or vacuum, multiplied by the radius of the sphere inside multiplied by the radius of the sphere outside, or how to term it better. Okay, so 4 pi epsilon naught multiplied by the radius of the outer radius of your inner sphere. So this is RA is for inner sphere, RB is for outer sphere, divided by the radius of your outer sphere minus the radius of your inner sphere, where RA is the outer radius of the inner conductor. When I say inner conductor, it's inner sphere, okay? Just the same. Do not get confused, outer radius, but inner conductor. And how about RB? It's inner radius and outer conductor. Later, I will show you a picture why we keep talking about outer radius of an inner conductor and the inner radius of the outer conductor. But just remember that when you're talking about RA, you're talking about your inner sphere or your inner conductor. When you're talking about RB, you're talking about the outer conductor or the outer sphere. For cylindrical capacitors, we use the equation capacitance is equals to 2 pi length of your cylinder epsilon naught divided by the natural log of the radius of your, again, this is for outer cylinder divided by the radius for your inner cylinder, where RA is the outer radius of the inner conductor or inner cylinder, RB is the inner radius of the outer cylinder, and L is the length of your cylinders. And assuming that L will always be longer or will always be higher than the difference between the radius of your outer cylinder and your inner cylinder. You have to make this assumption. You have to make sure that this is true in order for you to solve this. Otherwise, it will not, you won't get the correct answer. So why do we keep talking about the outer radius of an inner conductor and the inner radius of an outer conductor? So as you can see, this is, you have two, when we talk about conductors or capacitors, remember there's two plates. So imagine this red right here and this blue sphere right here as your two plates, but this time there's sphere. And one of the sphere is inside the bigger sphere. So you can see they have thickness right here. You see where the positives are written and the negatives are written. There is thickness, right? So when we measure the radius, when we measure the radius of your inner sphere, you have to include the thickness. That's why you're measuring the outer radius of your inner sphere. But when we're talking about your outer sphere or your outer conductor, you're measuring the inner radius. So meaning you're not including the thickness of your outer sphere. I hope that is clear. So when you're measuring the radius of your inner sphere or even your inner cylinder, you have to include the thickness of your cylinder or the thickness of your sphere. That's why we said outer radius, because this is the inner radius of your inner sphere. But you want the outer radius of your inner sphere, and then you want the inner radius of your outer sphere, because this is the outer radius of your outer sphere right here. So I hope that's clear. So two concentric spherical conducting shells are separated by vacuum. This is the picture. The inner shell has a total charge of positive Q, and the outer and its outer and an outer radius. So when they said outer radius of the inner shell, so you know the number that they gave you is correct, so you can use that. And the outer shell has a charge negative value and an inner radius of 10.5 centimeters. So you're talking about the inner radius of your outer shell, meaning they gave you the correct number. So you can write your given, and they're asking what is the capacitance of the spherical capacitor. Basically going to use this formula right here. So solution, so just plug in your numbers. 4 pi, this is epsilon naught, permittivity of free space or permittivity of vacuum or air. And this is your doesn't matter. So this is your inner radius and your outer this is your inner sphere and this is your outer sphere, and divided by the difference between your outer sphere minus your inner sphere. And that's how you solve for the capacitance of a sphere. Simple. No, this is your equation right here. The quantity 4 pi inner or the radius of your inner sphere and the radius of your outer sphere is an intermediate between the two areas. Because in the original equation for parallel, we use area, right? So when we try to measure for sphere, we have to also use areas, but we have two spheres. So we have two areas of two for each sphere, one for the inner sphere and one for the outer sphere. So we have to get the geographic mean between these two areas, and that is 4 pi r sub a r sub 2. So we don't need to worry about the area for each sphere, you just have to use the geographic mean between the two. And the distance between the two spheres is d is equals to rb minus ra. Why did I use the outer first minus ra? Because if you switch it, then you can have negative distance, and you don't want negative distance. You never have negative distance. So the equation, this equation right here that we use for spheres has the same for the equation that we use for parallel capacitors. So we have, this is basically the area of your two spheres, the geographic mean area between your two spheres. You have your area, you have your permittivity, and you have your permittivity, and you have the distance. And lastly, for cylinder, a cylindrical capacitor has an inner conductor of radius 1.5 millimeters. So this is your inner conductor radius. So this is your RA. And outer conductor radius of 3.5. This is your RB. The two conductors are separated by a vacuum, so you know that there's nothing in between them. The entire capacitor is 2.8 meters long, so meaning your capacitor has this length, so you have L. What is the capacitance per unit length? We'll discuss this later. The potential of the inner conductor is 350 millivolts, higher than that of the outer conductor. Find the charge and magnitude of both conductor. So you're given your RA and you're given your radius for your outer sphere or outer cylinder. And the length of your cylinders is 2.8. And you were given also the potential. The potential of the inner conductor is 350 MV higher than the length than that of your outer conductor. So this is their potential difference. So millivolts is equals to 10 raised to negative 3 volts. So they're asking about capacitance per unit length. And they're asking for the charge value for both conductor. So the formula you're going to use is this, which is the formula we discussed when solving for capacitance for a cylinder. And then we're going to use this as well. This is your very first equation that I told you about. When we measure capacitance, we just have one of the charge divided by the difference, potential difference between the two plates, but this time just the potential difference between the two cylinders. So solution, the capacitance per unit length is basically C over L, which can be derived from the equation of the cylindrical capacitors by multiplying both sides by L. So if we go back here, this is your equation. So you're looking for CL. So what you just need to do is divide both sides by L. You divide this side by L, you remove the L, you divide this side by L, so you get your capacitance per unit length. So capacitance per unit length, see there's no L there anymore. Substitute the number, you know this, and you were given this. You can solve for your capacitance per unit length. So is your capacitance per unit length. So 2 pi epsilon naught divided by the natural log of your RP, or the radius of your outer cylinder divided by the radius of your inner cylinder. We don't need to convert because they cancel anyway. So Q can be easily found using the equation C is equals to Q over V. We just rearrange. We know that the charge is basically equals to C multiplied by the potential difference. You were given the potential difference, but you are not given C. You solve for CL here, so you can use this to solve for C. So let's find C. So basically you have your CL, or your capacitance per unit length. So you just have to measure length on your capacitance per unit length to get C, right? Because you're given the length. Multiplying that will give you this capacitance. And since they give you the V, you can multiply your capacitance to the potential difference given, and you get your you get Q. So they were asking for both conductor. Does it really matter? Because I mentioned earlier that the magnitude of both plates or both metals should be the same. It's just one is positive and the other one is negative. So that's your answer. One is positive and one is negative. Just sorry, I forgot to add. So one of the other conductor is negative 6.4 times 10 raised to negative 11 coulombs. So that's it for capacitance and capacitors. So if you guys have any questions, feel free to message me and ask me. And I hope it's easy and clear enough for you guys and understand it. And we'll see you guys later for our virtual class. And I hope you guys have a great day. Thank you.